Okay, well, for all of you that were expecting PowerPoint slides, I do not have them. What I have are handwritten notes. Not only are they handwritten notes, but at the very top of it, it says, these notes were written on the Indian Pacific train to Perth in January 1986. Because I was going to Perth to go to the AUUG conference where I had agreed to give a talk on the history of BSD. And I figured, well, I have a 3-day train journey. Why not just write them on the train? So if you look at them, they sort of go like this a little bit. But and of course, this is only like the first 3 pages. I've had to add a little bit since 1986. In fact, it's gotten to the point where this talk actually takes 4 hours for me to give you the entire talk from end to end. But do not worry, we will not be here until 9 p.m. because we'd miss an hour of beer. However, in an act of shameless self-promotion, you can get the whole thing on DVD. 243 minutes is the running time, so you better have a large supply of popcorn and beer when you watch it. So these are available for $20. Just talk to me. All right, but getting back to the topic at hand here, clearly I can't cover the whole history. So there's sort of 4 tranches to the history. There's the early, how did BSD come into existence? Then there is what I call the TCP IP wars. So this was when we were developing TCP IP, and there was the Berkeley version, and the BBNN version, and the big showdown to decide which one was going to be the one. Then there's this little lawsuit that happened as we were trying to release the software to become the open source. And then there's sort of the modern, what happened once we did that release. So I'm not even going to offer the modern one because most of you were at least born by then, so you probably have some idea what that was. But I go by a show of hands whether you want to hear the early history, the TCP wars, or the lawsuit story. All of those, you can vote on multiple things, and I'm not going to like count all the hands. It's sort of, whichever one looks like it's the most hands raised. So how many people want the early history? Okay, that's a pretty good showing. How many people want the TCP wars? Oh, I think that's winning out here. How many people want the lawsuit story? Looks like we get TCP wars. Okay. You can always get the DVD if you want the rest of it. All right, so let's see here. We'll have to skip through all of that. Job control. Okay. All right, so we'll work our way forward. We have FreeBSD has gotten released, so there's all the BSDs that led up to that, but we'll assume that we're starting off with FreeBSD. And FreeBSD was it was a complete system, but it didn't have any networking in it. This is the system that we released in October of 1980. And so it was out there. It did not have the new file system, but it had a lot of other sort of robustness features in it. And it, best of all, ran on the VAX. So it'd gotten off the PDP-11 and was full-fledged VAX thing. And at this point in time, DARPA, which is the Defense Advanced Research Projects Agency, which is a fancy way of saying military money in the US that goes into research, decided that they had all these different contractors that were all running on different hardware with different operating systems and different programming languages, and nobody was able to exchange anything with anybody. And they really wanted to try and consolidate down to get sort of a particular piece of hardware that people were running and a particular bit of software, operating system, and so on. And they'd pretty much come to the conclusion that the VAX was the right piece of hardware. And so the real question was, would they run BSD on it, or would they run VAX VMS, which was the operating system from the vendor? And there was the two sides. There were the people that were adamant that they needed a real operating system with real vendor support, and that was VAX VMS. And then there was this contingent from Berkeley and some of the people that we had distributed our operating system to, who were adamant that it had to be BSD, and because this was, is supposed to be on research, and we were moving forward with this operating system. And so big war ensues as to which one it ought to be. And so there's this guy named Cashton who writes what we just refer to as the VMS paper, where he explains in excruciating detail why it is that it should be a VMS. And he finishes the paper with these 5 benchmarks that he runs on VMS and he runs on BSD. So one of them was like, how many get PIDs can you do per second? And VMS could do like 3 times as many as BSD could do. And how fast could you context switch was write 1 byte up and down a pipe as fast as possible. And on all of these things, VMS won out. And so Bill Joy, who was running the project at the time, gets this paper, and he just goes apoplectic, as only Bill is capable of doing. This is the stupidest set of benchmarks I could possibly imagine. How many people sit in a tight loop doing get PID? And but if that's the way they're going to make a decision, by God, we're going to fix it. So he goes in and fast pass get PID and various and sundry other things. And but the one thing that he just can't get down is the context switching, because he just it's written and it works, but it just doesn't run as fast as what VAX VMS has. And so how to deal with this? And I never got quite all the details of this story, but we were walking back from lunch, and there was this delivery truck parked in front of the building. And apparently, according to Bill, a package fell out the back of it. And it wasn't really clear who it was supposed to be going to. So we thought, well, maybe we'll open it up and there'll be like an invoice or something that we'll be able to make sure it gets to the right place. And it was filled with microfiche. And so maybe if we look at the microfiche, it might help us understand, a better idea of who was really supposed to get it, despite the fact that it said Computer Center on the label on the outside. At any rate, we looked at it, and the very first one we picked up was the assembly language for context switching in VMS. Amazing. Anyhow, we got the box delivered to the correct place, and miraculously, our context switching time became exactly the same as VMS. So Bill wrote his rebuttal paper, and DARPA decided that BSD would in fact be the correct solution to this problem. So they then proceeded to, well, we want to fund BSD. Well, BSD was like Bill Joy. Like, he was a graduate student, and this was just like a little side project that he did. In those days, we had 5 students in a single office, and we shared desks, and there was like 1 phone in the room. And if the phone happened to be on the desk that I was sitting at and it would ring, I would just pick it up and hand it to Bill because I knew it was for him. So Bill, besides doing like the development and sucking others of us in to work on various bits and pieces of it, was also like spinning tapes to send things out. It would run something like, you have an AT&T license, right? Yes, good, okay. Off would go the tape. So they needed a little more structure than this because it was going to be a more high-profile thing. And so they actually started, we actually created the Computer Systems Research Group, who were going to be the people that were going to, that group was going to get the funding, and Bill was going to actually be paid to do this kind of stuff, and there was going to actually be administrative assistants to like deal with answering the phone and actually checking that people had licenses and all that kind of good stuff. So anyway, there's sort of 4 things that were supposed to get put in as part of this project. Was, first of all, we needed networking. Well, we had networking, we had UUCP, but let's say a step forward from that. We needed to get the file system rewritten, we needed to get signal handling done in a way in which they were actually restartable, and we needed to get a virtual memory system. So we got 3 out of 4, which wasn't too bad. In fact, the DARPA people figured they'd be lucky to get 1 of them. Now, part of the deal was that they didn't really trust these, what they considered students at Berkeley, to actually understand how to do real networking. So they contracted with BB&N to actually write the TCP/IP protocols. And then what Berkeley was supposed to do was to come up with the API. So what we think of as the socket interface today. And I mean, in some sense, they say, yeah, the API is clearly unimportant. So you students can just figure out what the API is. You know, the core of this is the actual TCP/IP implementation. That's what we have to pay, you know, the big bucks for. So anyway, Bill Joy actually didn't know all that much about networking. So he designed the initial socket interface. But luckily, Sam Leffler was also at Berkeley, and he actually did know something about networking. And so he explained to Bill, you know, you have this accept system call, but like you can't take that socket and like tie it up on that port, because that would mean that you could only have one incoming connection for each port. You know, and you might want to have more than one SMTP connection coming in at the same time. And so they rev the protocol so that you accept now returns a connected socket, and you can immediately loop back around. I would say, you know, right there, if that hadn't been done, it would have been the end of the socket interface. Okay, so Bill, if nothing else, was really quick. Someone once asked me to compare myself to Bill Joy, and I said, well, you know, there's really nothing that Bill does that I couldn't do. But what Bill gets done in a month would take me a year. He's just like, I'm here, I want to get there. What is absolutely the shortest path from here to there? Now, someone else had to come along and clean up after him, but you know, he got there and it worked as long as you didn't change a single line of code. So anyhow, he got the socket interface all implemented, and he needed TCP/IP to put underneath it. And so he went to the folks at BB&N and said, well, I'm ready for TCP/IP. Where is it? And they're like, well, you know, we don't, it's not done yet. He said, well, do you have, you know, like a prototype or something that I could just, you know, start testing? I need to be able to test this thing, you know? And they're like, okay, well, you know, here's what we've got so far. And it was, you know, beautifully designed software. It was all really modular, and there was this state machine, and, you know, there was a routine for everyone, and a state manager, and all this stuff. So Bill drops this in, and it actually, it works. But the problem is that they were testing across a 50 kilobit backbone. That's what their test thing was, because that's what we had as the backbones for the ARPANET at the time. And if you took a VAC 750, which was about 0.7 MIPS, it running at 100% CPU could saturate a 50 kilobit line. But we had 3 megabit Ethernet, experimental from Xerox PARC, and you got 50 kilobits across 3 megabit Ethernet. And Bill's like, well, this won't do. What's going on? And he looks inside. It's like, oh, there's all this modular nonsense in here. You know, we'll fix that. One big switch statement, a few productive go-tos here and there. And by God, he had that thing so it could, at 100% CPU, saturate a 3 megabit Ethernet. Great. So everything is fine. We, of course, start shipping out. You know, there's lots of people that want this. So we shipped out something we called 4.1a. And that had this sort of hacked up networking stuff in it. And of course, people then immediately start using it and start sending back bug reports. And so we're tuning it and fixing it and so on and so forth. And so eventually, what ends up happening is that, you know, BB&N finishes their implementation of TCP/IP. And they say, okay, well, it's finished. Here it is. And Bill's like, it's okay, the one you sent us before is working great, you know, it's out in the field, and they're like, no, you know, you can't do that, you've got to have this, you know, this totally polished and ready to go one. And so Bill's response was to blow him off by going off to found Sun Microsystems. And so, and he suggested that I come along and I could be employee number 7 and I could get all this stock and so on. But I had gone through and gotten my Master's of Science in Business Administration, and so I knew something about startups. And so I explained to Bill that, you know, just coming up with a fancy new operating system, you know, it's not what people buy. You know, they buy applications, and Apollo has a 3-year jump on the market. They've got all the applications locked down. So, you know, Sun doesn't really, you know, I don't see how this is going to work. So if you have any questions about businesses, don't ask me. But meanwhile, Bill's gone, but Mike Carls has sort of taken over dealing with the networking stuff. And so Mike is sort of, he does a careful evaluation of the two different things, and he says, look, the functionality is the same. There's been a lot of work on performance and a lot of algorithm improvements and other things, and it's out there in the field. People understand and know this code. It's not helpful to drop in this later version from BBNN. We're fine. We'll just say it's BBNN's code. Don't worry about it. Well, BBNN, they have to justify the fact that they've received 7 times as much money as Berkeley has to do a third of what Berkeley was supposed to do. And so, they're like, no, you have to have this in here. And so we said, all right, fine. We will put both of them in there, and it'll just be a compile time switch. You decide, I want this version or I want that version. Well, even DARPA could see that this was a bad plan, right? The whole idea is to get people to converge on something, and having like half the people running one thing and half the people running the other thing is just like not where you want to go. So they said, no, you're not fooling us with that. We have decided, we've looked at the two ones, we have decided that the BBNN one is the one that you're going to ship. Now, I don't know how many of you know about this sort of free speech movement and so on that happened at Berkeley, but it just doesn't really work all that well to go to someone at Berkeley and just say, you are going to do this just because we pay you. And so basically we explained that, no, we weren't doing that. This did not sit well. But they also realized that we sort of had the upper hand because we, at the end of the day, were the people that were going to release this thing. And so they said, okay, what we need to do then is to have a bake-off. And we're going to go and find somebody that's going to be able to test the two of them, an unbiased third party that's going to go out and test the two of them and decide which one it is that is going to be done. And both sides have to agree that whatever this independent person decides is going to be the final answer. So then, of course, there's the huge debate as to who is going to be the person that's going to decide this. And well, BBNN, they have a lot more connections to the muck-a-mucks than we did. And so they pretty much got to pick who it was. And so they said, well, we found this guy, Mike Moose, at the Ballistics Research Lab in Aberdeen, Maryland. And they obviously have a lot to do with the DARPA stuff. And because they, BBNN had sort of selected them, and we got to say yes or no, more or less. And we were like, we don't even know this person. Okay, it's okay. We'll go with that, which was a lie. We knew him really well, actually. But so anyway, off it goes. And one of the big things for DARPA was they wanted to consider military settings for this code, which translated to what happens when you drop every 4th packet on average. I mean, not reliably every 4th, but approximately every 4th you just decide to drop it on the floor. And you have to do back off and retransmission and all the rest of it. And because, of course, that's what BBNN was saying theirs was really good at. So anyway, off it goes. And Mike Moose is running these experiments. And one of the experiments is where he sort of about a quarter of the time drops a packet on the floor in the driver. So, and then see what happens. So time goes by, and of course, he's not talking to anybody. His report comes out, and it is simultaneously sent to BBNN, DARPA, and us. And so, of course, the very first thing you do is go to the last page to see what the conclusion is. But he's smarter than that, and he doesn't put the conclusion at the end. You actually have to read about halfway through it before you find out. So anyhow, the upshot of this is that he says, well, on the tests where there's no packet loss, the Berkeley one clearly is far superior because it just has much higher throughput. He says, however, once we start losing a quarter of the packets, the BBN code does a much better job of recovering, and the connection throughput begins to be vastly in their favor until they panic. And the Berkeley code catches up during that period of time. Upshot was, his recommendation was that they go with the Berkeley code. Certain people at BBN still do not talk to me to this day. Okay, so that was sort of how we got to where we are in here. I'm just going to sort of finish out some of the other little interesting vignettes that went on there. The other one was that we were supposed to be doing was a file system. And so just so it's clear, both Bill Joy and I were getting our PhDs in programming languages. You might not guess that from looking at Seashell, but anyway, we both had the same advisor. When the DARPA project came in, Bill stopped working on his PhD and became a staff employee at the university and paid by the project. But I was still a student. And the way that the economics work, at least in the PhD program at Berkeley, is that you have this research student that gets fee, or your salary that gets paid by your advisor out of their grants. And the thing is that you get paid at 49.5% time, because that makes you less than a half-time person, so the university doesn't have to give you any benefits. But then in the summertime, when you're not theoretically taking classes, then you're allowed to get full-time for 89 days, because if it was 90 days, then they... Yeah. So what happens is that over the summer, your bank account builds up. You bank the extra money, and then all through the 9 months of the school year, your account is going down and down and down and down and down. And June is the month in which the first 2 weeks you're being paid at halftime, and the second 2 weeks you're being paid full-time. And so you should get sort of a 3/4 paycheck. And you're on fumes in your checking account, and you've got a stack of bills that you need to pay. So you're really looking forward to that 3/4 paycheck. So I, gasp to the June 30th, and my payroll thing comes in, and I've only got a quarter. And it's like, so they paid me for the first 2 weeks, and then I got nothing for the second 2 weeks. So I go down to the place where they deal with this stuff, and they say, oh, your advisor didn't, put in that you're going to be working over the summer. Just go have her, send us over the grant that it's supposed to come off of, and in 3 days' time, we'll make sure you get paid. Like, whew, okay, good. So I go up and I talk to my advisor and say, you need to get the summer grant down there because I need to get paid. And she goes, oh my goodness. She was really good about, various things, but little details like remembering to renew grants wasn't on that list. And so, it was clear she was going to get it, but she had to do some paperwork, and it was going to be a month, and I didn't have a month of savings. So I went down to Bill's office and I said, Bill, I explained the situation to him. I said, so I know you've got all this money from DARPA, so could you just put me on for the summer, and just give me some silly project to work on, and understanding that I'm going to really be doing my research, but I'll write a little paper or something, to finalize it at the end of the summer. And Bill, being the fiend that he was, he said, oh yeah, no problem, actually, I've got this little file system idea. If you could just kind of fill it out, and do a little prototype or something. Well, of course, I got sucked into that, and I spent the whole summer writing this file system. And at the end of the summer, I actually had something that I could demonstrate. And Bill goes, wow, this is great. It runs 10 times faster than the old file system. This is just totally awesome. it just needs like a little bit more work, and we could just like actually ship it. I said, what do you mean it needs a little more work? He said, well, you need to write FSCK and dump and restore and iCheck and nCheck and dcheck and FSDB and just a few little utilities. I mean, they already exist. You just have to adapt them. How long could it take? 18 months is the answer to that question. When I was being paid by my advisor to do stuff having to do with compilers, I was writing the file system. But maybe she felt guilty about that summer or something. Anyway, she didn't complain about it. In fact, I ended up writing a journal article about it, which is still widely cited to this day for reasons that I don't understand. So I said, well, in many ways, that ought to just be my PhD. Oh, no. PhDs have to be theoretical. This is just some stupid implementation. So I was not actually able to use it as my PhD topic. I wrote one on a really obscure thing about register allocation in table-driven code generators, which I think 3 or 4 people may have ever read. Anyhow, the upshot was that that's how the file system got done, and how I didn't end up being wildly rich and famous. So Bill also had this little idea about how the VM system ought to be done, and I was smart enough not to fall for that one. Instead, I actually did finish my PhD, and then by that time, of course, Sun was so big and far along that it wasn't really an interesting opportunity. And instead, I had the opportunity to take over and run the BSD group at Berkeley. So it seemed like a good idea at the time. And so I got started on that. And since the file system was finished, I could turn my attention to other things. And so there was the VM system. And following the usual algorithm of, don't come up with a good idea when you can steal a better one, we said, well, there's this mock project at CMU, and then Sun's already done another VM. And so we sort of analyzed those two and decided that the Sun one was probably a little bit better. But of course, we had to get permission from Sun to be able to incorporate that code. So you start by talking to the sort of the low-level manager type people, and then work your way up the chain, and eventually you get the VP of engineering to sign off on the fact that it's a good idea because there'll be co-development. And it got up to Scott McNeely, who was the head of the company at the time, and he thought it was a good idea, and so it got sent out to be drafted by the lawyers, and the lawyers came back and said, you're a public company, and you could be sued by your stockholders for giving away company assets. So that was the end of that. So we decided that mock looked okay after all. And it was an interface we didn't like on it, and there were all these ports and other things that made no sense to us. So we just brought it in, but we put it underneath the mmap interface that we had designed, and which was the same one that Sun had used. And so that's how the VM got done. And then, well, okay, VM is done. What shall I do next? And, well, there's this NFS thing that we need, and for that we need to put a VFS interface in, and I will duck so you don't throw tomatoes at me for how bad it is. But, it was being designed in the late 80s, so, and it has, I'm not responsible for some of the other random things that got done to it since then. Anyway, then working with Rick Macklem, got the NFS integrated in there. And that's when it suddenly struck me that you think you're done with projects, but you're not, because stuff comes in about the file system and you're expected to fix it, and stuff comes in about the VM system and you're expected to fix it, and stuff comes in about NFS and you're expected to fix it. And I was more or less on the front lines for all of those. So I, over time, managed to get rid of the NFS, and I got rid of the virtual memory, but I still seem to be on the hook for the file system. So that seems to be my life legacy. As I said this morning, if you had told me that code that I had written in the early 1980s was going to still be in wide production today, I would have thought you crazy. All right, so we managed to get these various and sundry things done. And then we announced 4.2 and finally got it out the door once DARPA had agreed to us. And so that release finally got out in about August of 1983. And we shipped actually 1,000 copies of that. And you have to remember, like, one copy goes to like an organization, and then the organization uses it throughout the organization. Now, this is also the same time as System 5 is starting to come out. So that in the 1950s, 1956 Dissent Decree, IBM agreed not to get into telephone business, and AT&T agreed not to get into the computer business. So they had this Unix thing, but they weren't allowed to do anything with it. So when AT&T monopoly got broken up, they got out of the Dissent Decree. So all of a sudden they could start marketing Unix, which they probably shouldn't have tried to do because they weren't particularly good at it. But nevertheless, they did. And so their first motivation was to, well, first of all, to try and co-opt us. So they said, well, we want you to, we want to work together and, we swap code back and forth and so on. But the problem was that the early licenses on which we were based, 32V, cost about $20,000 for a source license versus their new and improved one, which cost $250,000. And that was sort of too much money. And so we said, no, I think we'll just stick with the code we originally got from you so that we can stick with our original license. And so they got kind of cranky about this. And so what ensues after that is a lot of debate and other stories which eventually lead to a lawsuit. But I've gotten to the point where I sort of finished that previous story. So let's leave it at that, and I will take any sorts of questions, comments, and hopefully not too many rotten tomatoes. Come on, somebody has to have a question.
How to run a business?
Start by not getting an MBA.
You said you took over the CSRG group. Who was running it before you?
Well, Bill Joy had been running it before me, and then Mike Carls came over, and he and I sort of co-ran it. But since I had a PhD and he didn't, by university regulations, if you don't have a PhD, it's sort of like a union card that you have to have. So I was the investigator that was in charge of the project. But honestly, Mike and I pretty much ran it together. And later, Keith Bostick came in, and Keith Sklower. At our peak, we were 4 people, plus an administrator, 5. But we would just have meetings and sort of collectively decide who was going to do what and so on. So to say that I ran it was, the buck stopped with me. I got to write the stupid reports and things like that. But generally speaking, in terms of the technical decision, the 4 of us all worked together.
So during the TCP/IP stack development, the decision was made to actually do IPv4. That was the moment? Or?
Yeah, so actually, yeah, that's another interesting little story. Before TCP/IP came along, there was a thing called NCP, which was it was the first protocol that they actually ran across the ARPANET backbone. And it had an 8-bit address, because who could imagine having more than 255 hosts on the network? I mean, it would melt down if you had that many. So, because most institutions had like their VAX, or if you were like really rich, maybe you had 2 VAXs. But the point was that there was a small number of hosts, and so 8-bit address was enough. Well, it began to become clear that the next rev, to get to the next step, we needed more address bits. And the original Ethernet, the 3 megabit Ethernet, also had an 8-bit station address. And so when they decided to rev for the 10 megabit Ethernet, they decided to go to a 48-bit station address. And so it seemed like the obvious thing to do would have IPv4 with a 48-bit address as well. And so we were having the big debates as the IPv4 was being resolved was, should we have it as a 32-bit address or as a 48-bit address? And we at Berkeley were arguing for 48 bits. And we lost. That was one, there's these things that you win and lose, and it was one that we lost. So the argument against it was we're running on 50 kilobit backbones. Every single packet has a from and to IP address in it. So we were going to have 4 extra bytes overhead congesting these networks that were always going to be 0. And it was a waste of resources to do that, because 32 bits was enough for almost everybody on the planet to have an IP address. And I mean, that has to be enough. Anyway, we came very close to getting it. People say, if I had a time machine, what would I do? And they go back, well, I'd put an E on creat. The heck with E on creat. I'd go back and get 48 bits and IPv4.
You keep talking about all these things where you or somebody else won or lost. Are there any decisions that you won that you actually, looking back, wish the other person won?
Are there ones that I wish the other person had won? I was pretty adamant in what I wanted. Now, there are certainly ones that I thought were important that in the end really didn't matter all that much. But the ones you tend to remember the best are the ones you lost.
What happened to IP version 1, 2, and 3, and F5 for that matter?
I believe IP version 3 was the one that had 48-bit addresses in it. 1 was like the very first prototype, and I don't even remember ever seeing that. 2 was around, but it had like 16-bit, and it was like, no, that, everyone agreed. So, let's just go whole hog and go to, 48 bits. And then we got that pushed back, and so finally it settled down to the 32 that you see today.
What was your relationship to all these workstation vendors that were shipping some form of BSD, like, say the Sun clones and DEC that shipped Ultrix and all this kind of stuff? Were they just pulled from you, or?
For the most part, they were.
They never upstreamed?
Well, no, that's not true. Much of the structure that you see of the FreeBSD project today, we had actually back at the CSRG on a very reduced level. But we had put in place a source code control system. We had sort of the equivalent of committers was people that we trusted enough to give them accounts on the machine that the SCCS logs were on, so that they could actually commit stuff. And then they were responsible for pooling stuff from what we would think of as sort of developers today. So, for example, in the DEC Ultrix group, there was a couple people actually that had accounts on our machine, and they would upstream stuff, from DEC. Now, in those days, the rate of change of things was a much slower thing. So when we were getting ready to do a release, we literally went through the source code control system and printed the complete set of diffs of every change that had been made since the last release, and went through and audited it. It was a listing about that thick, which but it seemed like huge at the time, and think about what the listing would look like, and it'd be several piles of paper to the ceiling today. But it was because there were a much smaller number of people doing things, and it was a much smaller system. When I first wrote the fast file system, it was 1,200 lines of code, of which probably a third of it was the rename system call. If you were ever asked to implement the rename system call, just say no. I have rewritten it at least 4 times, and I'm sure it's correct now. Well, I'm almost sure it's correct now. Except that Scott keeps telling me that if you do some weird thing, it corrupts the file system somehow. But,
Was trailers a Berkeley thing, and if so, why?
Was which?
Trailers.
Trailers. Yes, trailers was a Berkeley thing. The idea of trailers was so that you could make sure that the data would, you knew exactly what the size of the header was, because it was just the Ethernet header. And so you could arrange so the DMA would come in so the data portion would start at the beginning of a physical page. And then we could just pass that up. And that was the reason we did it. Because copying on those machines was just very slow. Yeah.
Do you have any funny Clifford Stoll stories from working at UC Berkeley?
I don't actually have any good Clifford Stoll. I got lots of Van Jacobson stories, but because Clifford Stoll was sort of in a different time frame than when I was there, so I was not directly interacting with him.
Do you have any good Van Jacobson stories?
As chance would have it, I do. How much time do I have? Yeah, I've got time for a Van Jacobson story. So Van Jacobson at the time worked at Lawrence Berkeley Lab as a mathematician. And he was interested in networking, but that was not really where his primary focus was at that time. He was doing mathematical codes for things that go bang in the night. But part of the whole thing was he was starting to use the ARPANET at that point. And with 50 kilobit backbones, as you can imagine, round trip times of 15 seconds was not uncommon. And he was trying to understand why this was happening. And so he would try and come up with these models to understand on a mathematical level sort of about the flow of packets in a network. And much of the basis for a lot of the work that he did over time was really coming up with a mathematical model and then saying, okay, in this instance, where this identifies this problem, how would we go about fixing it? So he used to come down, and usually it was Tuesday afternoons, we would have a meeting where he would be there and we'd just be talking through stuff. And we had a big whiteboard that was more or less, all the way across the wall. And so he would come down with whatever his latest theory was, and he'd start, and he'd say, I think that we should model the flow of packets to the network like water through a pipe. And you have a pipe and it has a certain diameter, and of course it's not completely smooth on the inside, so there's a certain roughness. And so it turns out if you've got a pipe and you have water and you start increasing the pressure, you of course expect more water to flow through the pipe. And it does for a while, but at some point you hit a point where you just, it doesn't get any better, and in fact it can even get slightly worse. Because what's happening is as you put more pressure, it's flowing faster through the pipe, and so that the inside isn't completely smooth, and so you get these sort of back eddies going, and so it essentially constricts the diameter that the water can free flow through, and so as it goes faster and faster, it gets narrower and narrower, and so at some point it's a losing proposition. And so anyway, he says, so we're going to use the mathematical model for water flowing through a pipe to look at the flow of packets through the network. And so he starts out with, blah, 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 massive equations, mind-numbing, blah, da-da-da-da-da, on and on and on. And he finally gets down to the bottom. And so QED this. And it's like, great, what's that mean? He says, well, what it means is that you should add this if statement, if this is happening, blah, 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 do this little back off or, whatever. And so, you'd put that in and, we'd start testing it. And it would often work. One of my favorite ones was, we get to the end and so what should we do? And he says, well, you should just delete this code. It's like, great, that works for me. And then there was another one where we were trying to figure out when you should retransmit. And what we use is we're timing packets that are going, so we know what the average round trip time is. And we were using the average round trip time plus some epsilon. And he said, the problem is that some connections are very reliable. The round trip time is rock solid. And so if it hasn't gotten back there, very shortly after that round trip time, it's just gone. He says, in other places you have these networks that are really bouncing around, and the time is much less predictable. And so what we really need to do is track the variance, not just the average, but the variance as well. And then we'll use average round trip time plus 4 times the variance. So if it's got a low variance, we'll retransmit more quickly than if it's got a high variance. And Mike is like, Van, I think you've forgotten that variance is a transcendental function and it requires multiplications and divisions, and we don't really have those kind of resources available to us. And he goes, oh, well, you just use a Taylor series approximation. It's 1 over this and that times that, and then we'll just throw the rest away. Like, you've got to be kidding. That's like a horrible approximation. He goes, it'll be good enough, and it was. But the sort of my favorite one was there was something we were trying to do, and it wasn't exactly clear how to fix it. And he goes, well, I'll come up with some code and send it to you. And one of my favorite quotes from Van was that layering is a great way to design protocols, but it's a crappy way to implement it. And so it's like, well, yeah, we need stuff from 2 layers down, but that's okay. We'll just reach down there and grab it and do this and this. And so he came up with this code that admittedly ran much faster, but it was completely violating the layers and doing all this other stuff it shouldn't do. And so then Mike, who was like the antithesis of that, everything had to be picture perfect, would like straighten it all back out and figure out how to get the layer violations gone, and then Van would be, oh, you've destroyed my code, and he'd re-layer violate, and it'd sort of go ping pong, ping pong, ping ping, they'd eventually converge on something they could both be happy with. So those were very interesting times, and it got Van sufficiently interested in networking that he pretty much has done that ever since, to everybody's great advantage.
I've sat in meetings with him. He hasn't changed much.
Yeah, another one of my experiences is when he was giving a talk, and he really didn't like to stand up in front of an audience. Like, unlike me, you got to hold me off with a hook. Van, no. He did not like to give talks. So, and he's giving like the first talk of the morning. And so I'd arranged to get together and have breakfast with him beforehand because I knew he liked to, have some calm voice of reason explain that no, the world wasn't going to end when he stood up at the podium. And he orders a glass of wine at breakfast. And I said, am I missing something here? He says, no, it just takes the edge off of everything. I'm like, yeah, that it does, yes. But, I guess wine isn't just for dinner anymore.
The Van Jacobs changes were really interesting. I was at Convex when it started coming out, and I tried to get the people at Convex to look at it, and they were so small and sort of compartmentalized all over the stack that they were like, well, there's nothing here. Right? I mean,
Yeah, no,
really interesting tuning and sort of don't do that anymore.
right. No, most of Van's changes were very small, but had profound effects on things. All right, well, I think now would be a really excellent time to end because, I don't want to keep everyone from dinner because if you take too long at dinner, you're not going to get to the party by 8 p.m. And I expect you all to be there and drinking beer, which was supposed to be served here, but like flamethrowers and guns, they're not allowed in this building. And so we'll just have to defer until 8 p.m. Thank you very much.